So far what we have seen is we saw some kind of elaborative structures about the effective potential energy diagram, and also we define what's called as an effective force. Now I'm going to elaborate our earlier stated facts about the orbits, the characterizations of the orbits. We are going to interpret each and every orbit, which is circle, parabola, hyperbola, and ellipse. So let's start with circle. As being said, circle orbit or circular orbit. So we saw the condition was energy should be equal to the energy minimum, the minimum energy. So what it states is the lowest energy states corresponds to the minimum U effective. Let me write that down. Lowest energy state corresponds. This symbol stands for corresponds. It implies it means many more things. The lowest energy states corresponds to the minimum of U effective. Alright, this is very important. So the lowest energy state for us can be imaginable, but when we say we kind of a situation that we try to keep this differential equation intact. Right? So earlier I defined the effective force to be equal to the summation of the centrifugal force and the gravity. Now I am saying that the lowest energy states correspond to minimum potential energy. That means when I say the minimum potential energy, we get the minimum state only if the first order differential equation is set to equal to 0. We can find a minimum energy state when the first order differential with respect to this corresponding variable is set to 0. That's how we used to do in calculus when we used to find minima, maxima, and then we take the second order differential equation in order to find the sketches on the graphs exactly. So it's kind of a mathematical calculus deal. So what was U effective? Let me write it down before I forget. Hey, why I need to write down? I know this is nothing but the effective force, right? So I know the equation is L square upon mu r cube minus G m1 m2 upon r square. So when this is equal to this particular equation is 0, so that means 0 is equal to minus, and this is 0 at a particular point, which is r is equal to r naught, which corresponds that it is as an origin, that it is at the origin. R naught cube plus gm2 upon r naught square. Okay, I just changed the sign. It's not a big of deal. So it is equal to 0 here. I just changed the sign. It's okay. Right, we got r naught to be equal to L square upon G m1 m2. This gives me this particular equation. This particular equation gives me a circular orbit with radius r is equal to r naught. That's exactly what we saw a couple of videos ago, couple of lectures ago. So that's done. We have defined the circular orbit, which is corresponded by the equation energy minimum, and we stated that the lowest energy state will give you the minimum U effective, and U effective minimum can be given by if we set the first order differential equation the corresponding variable to be equal to 0, and we know the corresponding equation gives the effective force, and we can set that equal to 0, and thereby we can find the equation for r naught, and this will give us a circular orbit with the radius r is equal to r naught. That's done. Now the second thing is to find the elliptical orbit. This is one of the most, I have to say, it it is the most important the most important habit discussion that we are going to have, because this is exactly what we are going to take help if we have to learn the Kepler's law, because we are going through all this trouble just to learn what the Kepler's law is, and during that journey we are discovering many new things which are far intact if we hadn't pondered years ago. The energy, this is exactly what the condition was for the elliptical orbits. Now, I'm going to draw the diagram of the standard ellipse. Okay, my drawing is not so good, it's not done, but there is a point here. You see, there is a point here, and it makes an angle theta, and this is r. This is a standard ellipse. I have described the polar coordinates r and theta, and the point is over here. Now I will draw a figure which will correspond to this distance. This distance is what's called as the r minimum, and this vertical distance is what's called as r maximum. Alright, this is r minimum and this is r maximum. So just keep these two figures in mind. I'm going to elaborate this. So this condition corresponds to the minimum and the maximum values of r. So for an elliptical orbit, I mean just for r minimum, r maximum just correspond to the minimum and the maximum values. So let's see this from the energy perspective. Energy equation can be written as E is equal to L square upon 2 mu r square minus gm1 m2 upon r square. So I said r is equal to r minimum, and it is also equal to r maximum. Alright, I know this is kind of a done and done deal over here, but this is what the condition is. Now what I'll do is I can see clearly. See, I can see it clearly. It's a quadratic equation for r. It's a quadratic equation of for r. So I can redefine this equation in the following form. Let's go on to mu e is equal to 0. So now I can use the quadratic equation solution, which is, so I can get a solution rather than working through the mathematics. I'll just I'm not just writing the final answer directly, because I promised I will go through each and every step. That's what exactly I'm doing. I'm just leaving a small part to you, which is not big of a deal. L square upon 2 mu e. This is going to the r square root, because okay. Now what I'll do is I'll take this term common. You see, this term I'll take common, and I take common from this square root. So that's really helpful, because it helps me to visualize the eccentricity part very nicely. So I've taken common, I get 1, then plus minus sign. Here I have to take common this, and there is a square, so it will again give me 1, because the square and square root is 1. So in 2l square e square, and there is e and e square above, there is e and square, so it's e square goes here, so e square upon e, so that remains only e, and followed by pi mu gm1 m2 square. Okay, fine. Now this particular equation in the parenthesis is nothing but my sin. It's nothing but my eccentricity. So I define my R to be equal to minus G m1 m2 upon 2 times energy 1 plus minus epsilon. Oh, sorry, this is epsilon square. Yes, exactly. Because there is a square. This is epsilon square, and the square and this square root term is square, and the square root term it's cancelled, and we are left with only epsilon. See, you have to note this. The square root is only for this particular parenthesis. All right. It doesn't need to have this whole parenthesis. Just so we got an equation of R in terms of eccentricity and energy. Now I can further simplify because I know the value of R. I know R is equal to R naught 1 minus epsilon square upon, I also know I can write this equation as L square upon mu G m1 m2 upon 1 minus of 1 plus, see, 2 L square E. I'm just writing this equation, mu G m1 m2 square. Alright, now I can further simplify it. So by further simplifying, I can get Gm 2 m2 upon, there is a 2, the 2 term cancel, and I get minus 2 L square E, and there is this particular square term over here, and the right this okay, this particular term gets cancelled and it just goes above. I'll get a further simplified equation of minus G m1 m2 upon E. Yeah, I can forget the factor too. Let me rewrite this equation. See, if you haven't understood the mathematics here, the manipulations over here, I'll suggest just leave it, because if you ponder over a little things, you might be really scared to tackle some of the more important things that we have to tackle now. So I also described that the elliptical orbit is the most important orbit equation that we are going to look, but parabolic orbit is also a equally important thing. So let's not waste your mind. Do not waste your mind over understanding this particular equation. So I'm not telling it's not worth it. It's worth it, but don't do it at the expense of other understandings. That's what I want to say. So further, R is given by R naught 1 minus epsilon square. This term is nothing by R, because that's exactly what I took, right? So I can actually write this. Okay, just is equal to R naught upon 1. Oh, did I miss that factor? No, right? I don't miss this factor. If I take this down. Okay, yeah, it's nice, it's right. Yeah, it's minus epsilon square, and this particular equation over here would give me what's called as 1 plus minus epsilon, and further I can write this as 1 minus plus epsilon, because I can expand this term and I can just equate, I can cancel out this term, so I will left with minus plus, not plus minus. So what it's basically saying is we have R, so R minimum would be equal to R 1 plus epsilon, which is the distance of closest approach. distance of closest approach, which is also known as perigee. Secondly, if my r is equal to my maximum distance, which is this particular distance, we have just defined this r minimum, and if we have r max, so my equation for r max would be r naught 1 minus of epsilon, which is the distance of farther approach which is also known as apogee. So this was all about the parabolic orbit. I'm sorry, about the elliptical orbit. I know it was a little harder, but it's for the mathematics. Now we are going to state another equally important orbit, the parabolic orbit. The parabolic orbit is one of the most useful orbits that's currently being used by space agencies. So let's look at that term in detail. So the third one is parabolic orbit. So parabolic orbit energy is equal to 0 was the condition. So what I can use is, I can use the limiting condition. If my limit r tends to infinity over the effective potential will give me 0, which we know is true, because as u changes as 1 over r. So if r tends to infinity, my u would tend to 0. Similarly, my limiting potential in terms of kinetic term would give me 0. Thus, my energy will be equal to 0 in parabolic orbit as my r tends to 0. That means this path, okay, I'll tell you the meaning of this, but currently I want to know this path corresponds to the parabolic path. See, to escape from planet, I say if this is a planet and you want to escape this planet, the body must have energy equal to 0. Alright? Now the escape velocity for different kinds of planets. For example, the Earth, the escape velocity is equal to V escape is equal to 11.2 kilometers per hour. This is the speed that you need to escape Earth's orbit. So in order to the escape velocity condition corresponds to a parabolic path, to parabolic orbits in such cases. So we can actually state the energy equations, which is surprisingly easier, but it also equally more useful. Parabolic, right? Where we use the condition that the kinetic energy term is set to be 0, because we want to find the blah blah equations. So I'm using para over here because I just want to specify that it's a parabolic path and this is set to 0, because that's what our energy condition is, right? So my first claim was, I said the effective to be equal to 0 because of this limit. Secondly, my E is equal to 0 corresponds to the parabolic path, so I said E is equal to 0. Now I can find the R para, L square upon 2 mu G m1 m2 minus half R naught. Yeah, it's right. Okay, so let me rewrite this equation to give more clarity for you. Okay, parabolic path is L square upon 2 mu G m1 m2 minus R naught by 2. What does this imply? I mean, just looking at this equation, what can you say? See the minimum distance. I know you're not able to see it. I'll write here. The minimum distance. The minimum distance to the origin, but since we are dealing with the say some kind of a foci, foci is plural, is half the semi lattice rectum, because R naught corresponds to what is called a semi lattice rectum, as we defined it, as we are defining this term from way earlier. So this equation will give you my parabolic orbits. That's amazingly and that's surprisingly easy. Now my second, and my fourth and my last condition corresponds to what's called as hyperbolic orbit. Now hyperbolic orbit are not as useful as parabolic orbits, because one reason, if you toss some kind of a spaceship in a hyperbolic orbit, all you get is nothing. It just flies off. It just flies off to infinity. It won't return forever. And that's that's the laws of millions. Just to see a spaceship fly off for infinity, it's just a waste of millions of dollars. So this condition corresponds when energy is greater than 0. So when energy is greater than 0, my limitations in kinetic energy term as r tends to infinity will be 0. Now this corresponds to the equation of a hyperbolic orbit. Now I don't have those sheets here, so if you remember, a couple of lectures back I have wrote the described the orbits of each and every, I think it's 4b if I'm not mistaken. Yes, in 4b, in the lecture 4b, I have written all the 4 conditions. I mentioned the epsilon, energy, and also the energy equation. The general equation. Similarly, I'll do so from there. I'm taking this equation, Bx is equal to k, where I also define a is greater than 0 and k is greater than 0. Now there is only one positive solution. See, you should understand this, there is only one positive solution to this quadratic. Alright, it's a quadratic equation. It's viable, it's quadratic equation. To quadratic equation. So I can say that r square plus g m1 m2 upon e times r minus L square upon 2 mu E is equal to 0. This is E square plus 2, this is of the form, sorry, I'm writing E square. E square plus bx plus c is equal to 0. This will form x square plus, x square plus bx plus c, quadratic equation form. I don't know why I wrote a square, pardon me for that. So this is the same, same as in elliptical case, but only one solution. See, only one solution, only one positive solution. Thus I can define my r height is equal to r naught 1 plus epsilon. So as energy increases, so if you can see from this equation, as energy increases, epsilon increases, so distance of closest approach, right? We defined the closest approach distance, right, just 10 minutes ago, becomes smaller. Thus it flies off to infinity. So this corresponds to I have described all the 4 orbits in details, I worked out the required mathematics and we found the elliptical orbit was equally important as parabolic orbit, but the mathematics required for elliptical description was a little harder than the other. So, I want to show you this particular picture. So this particular picture, in this, we have all the four conditions. E greater than 0 describes the hyperbolic orbit, E is equal to 0 describes the parabolic orbit, and E minimum less than 0 corresponds to the elliptical orbit, and E is equal to E minimum describes the circular orbit. So this is how the graph looks like when we plot it U effective against R, and U is equal to 0 is just the straight line where we have represented all the R height, R para, R minimum, R naught and R maximum. R minimum and R maximum is viable with just extend this point to this point, you get this equation. I mean, just see how the particle is in elliptical orbit around this particular part of the graph. So this R minimum and R maximum are also called as the turning points, as you can see from the graph. But that comes under small oscillation, so don't have to worry